Okay, last time we talked about getting the equation of growth, and I think I put a problem very similar to this up on the board, and I hope I got the same numbers, but it doesn't really matter. The math building at a particular university, math department, there has a population of 250 rats, and it has been found that this population triples every 1.3 years. And what I want to do is find the equation of growth. That means I want to get something like n of t, the number at any time t, and I want an equation that describes the growth of these rats. Okay, well, what you do is you start out with the number you start with, you write that first, 250, that's what we found last time, that's where we put that. And then times, since it's tripling, it's going to be 3 to a power of t, but over how often it takes to triple 1.3, so I put 1.3 here underneath the t. And that gives me the equation of growth. And we did that by experimentation last time in the earlier lectures. We figured out that this was pretty much true by trial and error is what we really did. So now we have this equation of growth. And we're going to go over here and ask the two typical questions. And if you move the camera over, can you get a good slant on that, or you move it more direct? Doesn't matter. That's good right there. One of the questions is, how many rats will there be in 4 years? And here's our equation here. So we're really thinking of n at 4 for time. This equals 250 times 3 to the 4 over 1.3. And that will give us the number of rats in 4 years, just by putting in 4 in for time. And if I plug that in my calculator, I've done that already, and I get 7,345. 7,345. So in 4 years, I get 7,000 through. They grew pretty quickly, didn't they? Grew fast, all the way up to more than 7,000 rats from 250 rats. Okay. The next question of importance to us is, when will there be 70,000 rats? A lot of time you want to know, when will the population reach a critical point? And the way you do that is you put in 70,000 for this n of t, and you have an exponential equation to solve, which are a little tricky. 250 times 3 to the t over 1.3. I just copied the equation up here. Let me get this out of the way so you can see that I've got a new one here. And now I have to solve for t. And the way you solve for t in these exponential equations is you first isolate the exponential component there, that 3 to the t, that exponential term, 3 to the t over 1.3. That's 1.3 to make that better. So I divide both sides by 250. If I do that, I'm going to get 700 over 25. I'll cancel my zeros out. And this eventually reduces to, I think, 280 if you divide 25 into there. And over here I'll have 3 to the t over 1.3. And notice my exponential term here is isolated. Once you have your exponential term isolated, you take the log of both sides. So I'm going to take the log of this left side. Remember, this is, what did I say it was? It was 280. If you divide 25 in there, you get 280. That's an easier number to deal with. Should equal the log of 3 to the t over 1.3. And we're getting close now. We're getting close here. So we want to know when there will be 70,000 rats. I'll erase this so I can get down here, because we know the question. And now what I can do is use one of the exponential law of logarithms, that I can bring the exponent out front, and I get the log of 280 equals t over 1.3 times the log of 3. That's what I've got left over there. Now this is really t log of 3. Remember, log of 3 is a number over 1.3. It's a little linear equation. I solve for t. I bring the 1.3 up here. 1.3 log of 280, and I bring the log of 3 down here. What did I say? 1.3 up here, the log of 3 down here, right? And this is what my time is. This is how long it's going to take me to get to 70,000 rats. And if I pop this in my calculator, I get a time of 6.67 years. So this poor university math department is in trouble. in 6.70 years, 6.67 years, they're going to have 70,000 of these rats unless they start poisoning them.